Well, what about the lateral modes? That's the longitudinal modes. If you did the same thing with the lateral modes, then you will end up with these equations here, which is this is the last page of my handout. And again, these equations are the same that you see as in Nelson. These are exactly the same equations, or in Roscoe. So now notice I have V, which is side motion, phi, which is rolling motion, and r, which is yawing motion. Side phi and r. So if I put them in that equation, I get the same determinant structure. Except that when I compute the determinant of equation 78, this is for the longitudinal mode. For the lateral mode, I'm going to get a different set of roots. For the lateral mode, I will get roots that look like this. I'll get one out here, and that's usually called the roll mode. So this value is usually minus 1 over the roll mode time constant. We'll talk about what that means in a second. Then we'll have a mode close to the origin, a very slow mode that's called the spiral mode, like so. So this again, we're talking about the lateral perturbed equations of motion is what we're talking about now. And then you'll have a set of oscillatory modes that are called the Dutch roll poles. So that's what you're going to get for lateral modes of motion. Again, the numerators that you pick will depend on what your transfer function is going to be. I'll get different numerators depending on which transfer function I want to express here. But I will always have the same poles. Right? And they're different than the longitudinal poles. Not related at all. Totally independent set. Physically, what is it? This roll mode is easy to figure out, isn't it? I move my stick to the side, and the airplane is going to roll. How fast does it get to 63% of its final value of roll rate? See at first order? We remember now, right? We know that the response of this to a step input, right, looks like this. So if this is my roll rate command, then this is my roll rate command is dashed, and this is my roll rate. It's like an actuator, right? Move the stick like that, I'm 72% of my final value of roll rate. That's what that means. The spiral mode means if I put the airplane in 10 degrees of bank and let it go, just watch it. Will it roll back to level flight real slowly? Or will it roll over and go into the drink? Well, if this is slightly to the left, it will roll back to level flight. If this is slightly to the right, it will roll over into the drink. So the spiral mode can be stable or unstable, but it's going to be very slow. Most pilots don't even notice it. Dutch roll mode, if you step on the rudder, you'll have a coupling between yawing and rolling motion. It looks like this. And the name comes from Roscoe. Roscoe was a Dutchman. And Roscoe said it's like a Dutchman walking home after the tavern with wooden shoes in the tunnels or of Amsterdam. So Dutch roll has that same rolling oscillation motion that Roscoe gave it as a name. So that's your oscillation. So that normally would be bad on a passenger airplane, especially if you're sitting in the back. Yeah. So all big airplanes have a horrible Dutch roll that you have to get rid of. Your control system has always had to get rid of the Dutch roll in the big airplane, even from the 50s or 60s. Okay, got it? Well, let's see if we can do an exercise now. And two things I want you to remember from this class that you have to remember, put in your pocket. How to get the Kramer's rule notation. Right? So example, if I said, what is P to delta A? What's that transfer function? P to delta A. What do I do? Well, I take the determinant of the left side of equation 78, and I call that del lat, yes? I call that del lat. It's going to be a fourth or fifth order polynomial in S. How do I get the numerator? Take phi. So I would replace the second column with the first column there, the delta A, and that would give me phi of S, which would be n phi delta A of S. Now letting you off the hook, exam question. What's P of delta A? I got phi of delta A. What's P of delta A?
Same thing.
No.
It's
How are they related? How is phi related to P? Derivative, yes? How do I take the derivative in the Laplace domain? How do I take the derivative? So if I wanted P, do I just do that? Yep. Okay. So if you know what phi of S is, and you want the P of S, you just multiply the numerator by the derivative, and you've got P of S. Same with theta and Q. All right, so let's go back and do what is N, R, R. Right? What is that? That's stability derivative. This guy right there. Well, come on, it's exam time. I just asked you a question. This is what is NRR in terms of the book? If you look in the book is going to give you what? The book's going to give you C, N, R. So you have to be able to relate these two for all the stability derivatives, for all of them. So let's do this one. Should I do it? Okay. How about the name of it? Yaw motion due to yaw rate. Right? It's yawing torque due to yaw rate. Yaw rate is R is this way. If I have a yaw rate R, my vertical fin is going to act like a damper, yes? The bigger the vertical fin is, the more it's going to be like molasses going through the air. So I'll have an opposing torque. I'll have an opposing torque whenever the bigger R is, the bigger the opposing torque is, right? So that's yaw damping. This is yaw damping. So this is called yaw damping. It's negative because of the physical thing that I just showed you, right? It equals, and this is where your memory has to come in, 1 over IZ, right? You're normalizing by Z, partial N over partial R. Evaluated at the equilibrium condition. Okay? So this is going to be equal to 1 over IZ, partial Q bar, S, B, C sub N over partial R. That's dimensionless. We just took the dimensions out. Dynamic pressure, wingspan. We're with me? With me, everybody? Okay, so then we're going to take out the Q bar SB over IZ. We're going to take that out. And now I've got partial C sub N over partial R, but I got a problem, don't I? R has units, radians per second. Screws up my stability derivative. So it's got to be R hat, partial R hat over partial R. And I have to define R hat so it has no units. So we pick R hat equal to B over 2, the steady state velocity, times R. Right? This is a convention that you take your R hat to be. So I can replace my partial R hat over partial R, right, with B over 2B. So I can replace this guy. Becomes B over 2BT1. Right? So then the end result will turn out to be Q bar SB squared over 2IZ BT1 CNR. That's how you relate the dimensional derivative to the dimensionless coefficient through this. What's the secret handshake? What's the secret handshake? I just threw it by you. I blew it by you. What was the secret handshake? R hat. So how come I got CNR? That's the secret handshake. It's CNR hat. Right? It's CNR hat. That's what you have to know. Guess what? He won't tell you that. He's going to give you CNR, but you're going to know from the secret handshake it's what? It's CNR hat. Right? If it's CNR, then this is going to have units on it. Make sense? Okay, so you have to remember that this is R hat, not R. That's the secret handshake. Okay, ready? See you